Not quite, because on October 29, 2025, when 3I/Atlas made its closest approach to the Sun, something happened that split the scientific community right down the middle. The object deviated from its predicted path. Not by a lot, not by some dramatic swerve that you could see with the naked eye, but by enough, 4 arcseconds off in one direction. That is a tiny, tiny measurement. But in the world of precision astronomy, that number might as well have been written in neon lights. The data came from ALMA, the Atacama Large Millimeter Array in Chile, one of the most powerful radio telescope systems on the planet. And what ALMA was telling scientists was simple but deeply unsettling. 3I/Atlas was not where it was supposed to be. If you calculated its path using gravity alone, the gravity of the Sun, the gravity of the planets, all the known forces acting on it, the object should have been in one spot. But it was in a slightly different spot. Something other than gravity was pushing it. The data came from ALMA, the Atacama Large Millimeter Array in Chile, one of the most powerful radio telescope systems on the planet. And what ALMA was telling scientists was simple but deeply unsettling. 3I/Atlas was not where it was supposed to be. If you calculated its path using gravity alone, the gravity of the Sun, the gravity of the planets, all the known forces acting on it, the object should have been in one spot. But it was in a slightly different spot. Something other than gravity was pushing it. Before the perihelion non-gravitational acceleration was detected, there was actually a separate but related puzzle. Between May and September 2025, when 3I/Atlas was being tracked by over 4,000 observations from 227 observatories worldwide, the object showed no detectable non-gravitational acceleration at all. 0, the upper limit was tiny, about 0.028 arcseconds of positional shift over 4.5 months. Given that the Webb Space Telescope had already measured gas coming off the surface at a rate of about 150 kilograms per second, the absence of any measurable push meant the comet had to be extremely heavy, at least 33 billion tons. With a solid density nucleus, that would mean a diameter of at least 5 kilometers. This was a problem. If 3I/Atlas was that massive, it would be 3 to 5 orders of magnitude heavier than Oumuamua and Borisov, the two previous interstellar visitors. Given the limited reservoir of heavy elements available to form such objects, you would expect to discover hundreds of thousands of smaller interstellar objects before finding one this big. Yet we had only found 2 before it. The statistics seemed wrong. Then perihelion happened, and suddenly there was a non-gravitational acceleration, which actually brought the mass estimate down to something more reasonable, around 44 billion kilograms, consistent with a nucleus of about half a kilometer to 3/4 of a kilometer in diameter. The Hubble nucleus detection, in January 2026, confirmed a size of roughly 1.3 kilometers. The numbers were starting to converge, but Loeb pointed out the whiplash. First, the object was anomalously massive because it showed no acceleration. Then it showed a lot of acceleration, and the mass estimate dropped. The story kept changing, and in his view, a story that keeps changing is a story that has not been fully understood. Now, this by itself is not necessarily strange. Comets do this all the time. When a comet gets close to the Sun, the heat causes the ices on its surface to sublimate, to go straight from solid to gas. That gas shoots out into space, and by Newton's third law, every action has an equal and opposite reaction. The gas goes one way, the comet gets a tiny nudge in the other direction. Scientists call this non-gravitational acceleration. It has been observed in dozens of comets in our own solar system. It is well understood, it is not mysterious. But here is where the debate begins. David Farnokia, a navigation engineer at NASA's Jet Propulsion Laboratory, was one of the first to officially report this non-gravitational acceleration for 3I/Atlas. His analysis showed 2 components, a radial acceleration pushing the comet away from the Sun, and a transverse acceleration pushing it sideways, both measured at perihelion, the point of closest approach to the Sun, at a distance of about 1.36 astronomical units, roughly 203 million kilometers. For most planetary scientists, this was expected. The comet was getting blasted by solar radiation. Its ices were boiling off. The resulting jets were giving it a push, nothing unusual. But here is the thing that most people miss about non-gravitational acceleration. It is not just about whether it exists, Every comet expert agrees that comets get pushed around by their own outgassing. The real question is whether the amount of acceleration matches the amount of gas being produced. Think of it like this. If someone tells you a car is going 60 miles per hour, you would expect to see an engine under the hood that is capable of producing that speed. If you open the hood and find a lawnmower engine, you know something does not add up. The acceleration is real, but the engine is too small. That is essentially the argument that one side of this debate is making, and that brings us to Avi Loeb and his calculations. Loeb, the Harvard astrophysicist who has been at the center of this debate since the very beginning, took the measured acceleration and applied a simple physics principle: momentum conservation. If the non-gravitational acceleration was caused entirely by outgassing, by gas being ejected from the surface, then you could calculate how much mass the comet would need to lose to produce that much of a push. And the number he got was staggering. At least 10% of its total mass, perhaps as much as a sixth, lost in the span of roughly 1 month as it swung around the sun. If 3I/Atlas had a mass of around 33 billion tons, which earlier analysis had suggested, then we are talking about billions of tons of gas being expelled into space in a matter of weeks. Now that kind of mass loss should be visible, very visible. If you are dumping billions of tons of gas into the vacuum of space, you would expect to see an enormous cloud surrounding the comet, a massive plume that telescopes could easily detect. Loeb argued that if this gas cloud was not observed during November and December 2025, when 3I/Atlas was closest to Earth and being watched by hundreds of telescopes, then outgassing could not be the explanation. And if outgassing was not the explanation, then what was causing the acceleration? This is where things get controversial. And honestly, this is where the debate goes from being a normal scientific disagreement to something much bigger, something that touches on how we do science itself, what counts as evidence, and who gets to decide what questions are worth asking. Loeb suggested that the non-gravitational acceleration could be the signature of a propulsion system, an engine, something artificial. He pointed out that this was exactly what happened with the first interstellar object, Oumuamua, back in 2017. Oumuamua showed non-gravitational acceleration too, but it showed no gas, no dust, no coma, nothing that would indicate cometary activity. The Spitzer Space Telescope looked for infrared signatures of outgassing and found nothing. And yet the object was accelerating away from the sun in a way that gravity alone could not explain. Scientists eventually labeled it a dark comet, a comet that produces no visible tail. Loeb called that an oxymoron. A comet without a tail is like a fish without water. It does not make sense unless you consider the possibility that it was not a comet at all. There was also the color change to consider. As 3I/Atlas approached perihelion, its color shifted dramatically. It went from a reddish hue to something bluer than the sun itself. Now for a comet, this is very unusual. Dust around a comet typically reddens the scattered sunlight, and the surface of 3I/Atlas was roughly 20 times colder than the sun's photosphere, so it should have appeared redder, not bluer. Loeb pointed to this as another piece of evidence that something unusual was happening. The brightness also surged rapidly, scaling inversely with distance from the sun to the power of -7.5. That is an extraordinarily steep brightening curve, much steeper than typical comets, but the mainstream scientific community pushed back hard. Jason Wright, an astrophysicist at Penn State University, published a detailed response addressing what he called Loeb's anomalies one by one. On the question of non-gravitational acceleration specifically, Wright argued that the measurement itself was not as solid as Loeb was treating it. The problem, Wright explained, is that 3I/Atlas is fuzzy. It is surrounded by a coma of gas and dust that makes it difficult to pinpoint exactly where the nucleus, the solid core of the comet, actually is. When you are measuring the position of a fuzzy blob of light against the background of stars, your uncertainties are larger than they might appear in the data. Many planetary scientists, Wright noted, were skeptical about the statistical significance of the detection, and even if the measurement was correct, Wright argued, losing 13% of its mass was not particularly strange for a comet. Comets are fragile objects. They are loose collections of ice and rock held together by relatively weak forces. When they get close to the sun, they can shed enormous amounts of material. Some comets have been observed breaking apart entirely. The idea that 3I/Atlas lost a significant fraction of its mass during a close solar encounter was not, in Wright's view, anything that required an exotic explanation. Megan Schwamb, a professor of planetary science at Queen's University Belfast, made a similar point. She told reporters that if there was an increase in the rate of volatile ices sublimating off the surface, then the comet would naturally speed up. This happens with long-period comets, short-period comets, and it happened with Oumuamua too. The physics is straightforward, but then new data started coming in, and it made things more complicated, not less. In November 2025, NASA's JPL Horizon system updated the non-gravitational acceleration parameters for 3I/Atlas, and this update itself became a source of controversy. The radial component was revised downward by a factor of 6. The model was also changed from one based on water-ice sublimation to one based on carbon dioxide sublimation, which follows an inverse square law with distance from the Sun. This was significant because JWST had already confirmed back in August 2025 that 3I/Atlas had an unusually high ratio of carbon dioxide to water in its coma. The CO2 to water mixing ratio was 7.6 to 1. That is among the highest ever observed in any comet, several standard deviations above what is typical. Loeb was not happy about the timing of this revision. He claimed that he had emailed David Farnokia at JPL about the Hill radius coincidence, and within a couple of days, the acceleration parameters were changed. He compared the situation to the Vatican, insisting that the Earth was at the center of the solar system, saying that changing the model on paper does not change the actual trajectory of the comet. Whether that comparison was fair or not, it certainly added fuel to an already heated debate. Now, why does this matter for the non-gravitational acceleration debate? Because the type of ice that is sublimating determines how the acceleration varies with distance from the Sun. Water ice sublimates aggressively only when a comet is relatively close to the Sun, inside about 2 or 3 astronomical units. Carbon dioxide, on the other hand, can sublimate at much greater distances, out to about 5 astronomical units. So if CO2 is the dominant driver of the outgassing, then the acceleration profile changes. It is more spread out, it peaks differently, and crucially, it changes the predicted trajectory of the comet. Loeb noticed something striking about this revision. When the previous model was used, the predicted closest approach of 3I/Atlas to Jupiter in March 2026 matched almost exactly with Jupiter's Hill radius, the boundary of Jupiter's gravitational sphere of influence. The Hill radius is the distance from Jupiter within which its gravity dominates over the Sun's gravity. For Jupiter, this is about 53.5 million kilometers. According to JPL's calculations, 3I/Atlas would pass Jupiter at a distance of 53.445 million kilometers, plus or minus 0.06 million kilometers. Jupiter's Hill radius at that time would be 53.502 million kilometers. These two numbers are essentially identical within the uncertainty. A coincidence of roughly 1 part in 1,000. Loeb found this remarkable. The non-gravitational acceleration that 3I/Atlas received near the Sun, the very acceleration that was being debated, was exactly what was needed to nudge the comet's trajectory, so that its closest approach to Jupiter would land right at the boundary of the planet's gravitational domain. If you wanted to deposit something into Jupiter's gravitational sphere of influence, this would be precisely the trajectory you would design. He went further. If 3I/Atlas was some kind of mothership, a technological artifact from another civilization, then the jets observed around the comet could have been used for precisely this kind of orbital correction. And the fact that 3I/Atlas was hidden behind the Sun during its perihelion, when it gained most of its non-gravitational acceleration, meant that Earth-based telescopes could not watch what was happening during the most critical phase of its journey. The scientific community, predictably, did not take kindly to this line of reasoning. Dan Green from the Harvard-Smithsonian Center for Astrophysics stated that non-gravitational forces were not necessarily even present in the way Loeb was describing. With more Earth-based observations being made as the comet pulled away from the Sun, the situation would become clearer. Tom Statler, NASA's lead scientist for solar system small bodies, acknowledged that the data showed some changes to the orbit, but emphasized that the uncertainties were still fairly large. Until astronomers could clearly resolve the nucleus of the comet and separate it from the surrounding coma, pinning down the exact position to the precision needed for these claims would remain difficult. Meanwhile, a study by Florian Neukart attempted to explain the non-gravitational acceleration entirely through conventional cometary outgassing. The paper argued that for realistic active fractions and jet collimation, meaning if you assume a reasonable percentage of the comet's surface is actively ejecting gas, and those jets are somewhat focused rather than random, then you can reproduce both the magnitude and the direction of the observed acceleration. No exotic physics required, no alien engines, just ice turning into gas and pushing the comet. And then December 2025 arrived. This was the month that Loeb had said would be the test. If cometary evaporation was responsible for the non-gravitational acceleration, there should be a massive gas cloud around 3I/Atlas, billions of tons of material that telescopes should be able to detect. What actually happened was more nuanced than either side probably expected. NASA's FAREX Infrared Space Telescope observed 3I/Atlas in December 2025, about 2 months after perihelion, and what it found was dramatic. The comet was, in the words of the FAREX team, erupting into space. Water vapor, carbon dioxide, carbon monoxide, methanol, hydrogen cyanide, methane, and even rocky material were all streaming from the nucleus. The brightness had increased sharply compared to earlier observations. Fresh volatile rich material from beneath the surface was being exposed for the first time as solar heat penetrated deeper into the nucleus through thermal conduction. This delayed eruption was explained by thermal inertia. Think of it this way. When you heat a brick wall on one side, it takes time for the heat to travel through to the other side. The outer crust of a comet works the same way. It is an insulator, the sun blasts the surface, but the heat takes weeks to work its way down to the deep interior where the really pristine, volatile-rich ices are buried. Ices that have been frozen solid for billions of years. By December, that thermal wave had finally reached those ancient ice deposits, and the result was explosive. The most intense outgassing event since perihelion. There was more. The SOHO SWAN instrument measured a remarkable asymmetry in water production around perihelion. On the way in, water production increased incredibly steeply, following the inverse 5.9 power of the distance from the sun. That is an extremely steep ramp-up. But on the way out, water production declined much more gently, following only the inverse 3.3 power. The comet stayed active far longer than a simple solar heating model would predict. Peak water production hit approximately 3.17 times 10 to the 29th molecules per second on November 6, about 1 week after perihelion. That delay between closest solar approach and peak outgassing was direct evidence of thermal inertia at work. For the mainstream camp, this was vindication. The comet was outgassing massively, just as expected. The non-gravitational acceleration had a perfectly natural explanation. Gas was coming out, lots of it. But Loeb was not convinced. He pointed to the timing, the distribution, and the composition of the outgassing. He noted that the JWST had just detected methane in the coma of 3I/Atlas, the first time methane had ever been observed in an interstellar object. Methane is a hypervolatile substance. It sublimates at much lower temperatures than carbon dioxide. The delayed onset of methane production raised questions about the thermal history of the comet and whether the outgassing patterns truly matched what you would expect from a natural body. And then, in late January 2026, Hubble finally achieved something astronomers had been trying to do for months. It directly detected the nucleus of 3I/Atlas. The team led by Manto Hui used careful image processing to subtract the glow of the coma and isolate the signal from the solid nucleus itself. The result placed the nucleus diameter at roughly 1.3 kilometers. This was consistent with earlier estimates from the non-gravitational acceleration data, which had suggested a nucleus mass that would correspond to a body of about that size if it had a typical comet density. This was actually important for the debate because it meant the mass of 3I/Atlas could now be better constrained. And if the mass was known more accurately, then the amount of outgassing needed to produce the observed acceleration could be calculated more precisely. The numbers, according to most planetary scientists, were lining up with natural cometary activity. But there was another finding that complicated the picture. The rotation period of 3I/Atlas had changed dramatically. Before perihelion, ground-based observations in July 2025 measured a rotation period of about 16 hours. By late January 2026, Hubble photometry and TESS light curve data both showed a rotation period of approximately 7.1 hours. The nucleus had more than doubled its spin rate. This spin-up was caused by outgassing torques. As asymmetric jets of gas and dust erupted from the surface, they acted like tiny rocket engines, applying angular momentum to the nucleus. Three symmetric mini-jets, separated by about 120 degrees, were visible in Hubble images, wobbling back and forth with the rotation. The rotation axis appeared to be nearly aligned with the Sun-comet direction. Now, extreme spin-up can actually threaten the structural integrity of a comet. If the centrifugal stress exceeds the tensile strength of the nucleus, the whole thing can fly apart. This was being closely monitored. For the natural comet camp, the spin-up was yet more evidence of powerful outgassing. The jets were clearly there, clearly active, and clearly affecting the comet's motion and rotation. This was exactly what you expect from a comet being heated by the sun. For those in the other camp, the precise geometry of the jets and the dramatic change in rotation raised additional questions about the internal structure of the object. And now, as we approach the middle of February 2026, the scientific community is looking ahead to two critical events. First, ESA's JUICE spacecraft is expected to downlink its observation data between February 18th and 20th. JUICE passed within observational range of 3I/Atlas during its gravity assist trajectory in November 2025. It may have captured the closest ever observations of an interstellar body, but because JUICE was using its main antenna as a heat shield while close to the sun and could only transmit data at a low rate through its smaller antenna, the scientific data has been waiting months to reach Earth. Whatever JUICE saw could significantly advance our understanding of the comet's activity, its gas production, and its physical properties. Second, and perhaps more dramatically, March 16, 2026 is approaching. That is the date when 3I/Atlas will make its closest approach to Jupiter. Whether that distance matches Jupiter's Hill radius, as Loeb predicts, or falls somewhat outside it, as the revised JPL models suggest, will be a major data point. There is an interesting counter-argument to the Hill radius coincidence that is worth mentioning. Jorge Abreu-Vicente, an astrophysicist who analyzed the orbital mechanics in detail, pointed out that Jupiter has many special radii, not just the Hill radius. There are Lagrange points, various gravitational boundaries, and the orbits of its many moons. Any hyperbolic flyby would cross through all of them. Using a Monte Carlo simulation of random interstellar trajectories passing by Jupiter, he argued that passing near the Hill radius was not as statistically remarkable as Loeb made it sound. He also pointed out that if an advanced civilization actually wanted to study Jupiter, they would target the stable Lagrange points, where a spacecraft could remain indefinitely with minimal fuel, not the unstable Hill radius boundary where an object would drift away without constant correction. Juno, the spacecraft currently orbiting Jupiter, may be able to image the comet during the encounter, though it is running low on fuel and has engine issues. Even a low-resolution detection from JunoCam would provide the first close-range look at an interstellar body and could help settle the nucleus size debate once and for all. The non-gravitational acceleration debate around 3I/Atlas is at its core a debate about how we interpret data. On one side, you have a well-established body of cometary science that says icy objects near the sun lose gas, and that gas pushes them around. On the other side, you have a smaller group of scientists who say the numbers do not quite add up, that the coincidences are too precise, and that we should at least consider the possibility that we are looking at something we have never seen before. What is remarkable about this moment in science is that we actually have the tools to settle the question. We have Hubble and Webb in space. We have ALMA and the Very Large Telescope on the ground. We have JUICE and Juno and Psyche and Europa Clipper and Parker Solar Probe, all of which have contributed observations. We have TESS and SPHEREX and SOHO and PUNCH. The sheer number of instruments pointed at this one object is unprecedented in the history of astronomy. The data is coming in, and it will keep coming in through March and beyond. The beautiful thing about science is that it does not care about opinions or authority or popularity. It cares about measurements. And right now, 3I/Atlas is giving us more measurements than we have ever had for any interstellar visitor. Whether those measurements ultimately point to a natural comet that formed around a distant star billions of years ago, or to something else entirely, is a question that will be answered not by arguments or speculation, but by the quiet, relentless work of observation. The universe has sent us something, and for the first time in human history, we are actually equipped to figure out what it is. We just have to be patient enough to let the data speak.